Welcome! This video is on laser ablation and drilling. It will turn out that it will be more or less basically on drilling and that we will have a second one of ablation. But since the general subscript of these processes is ablation, we start with the ablation itself. So as a content, you see in this list we have first of all some applications of laser ablation, and then the ablation process, different laser drilling processes like single laser drilling, percussion drilling, trepanning, and helical drilling. And as an outlook, we will take a look at what I just mentioned at the sub-wavelengths structuring and ultrafast precision ablation. A few examples for motivation. There are a lot of applications from marking, from medical applications, eye surgery, to cleaning applications, house cleaning, industrial cleaning, structuring, surface structuring, nanostructuring of surfaces, and in the more deep applications of materials processing, laser drilling. The ablation process can be structured in basically two domains. The first one is the melt-dominated domain, in which we melt a typical surface to form a melt pool and then increase the temperature such that we get a vaporization and consequently a vapor pressure which pushes out the melt more or less around the laser-induced plasma, which generates the pressure. As a result, we will find a processing geometry which basically will depend on the resolidification of the melt, so it will have rather melt-dominated geometries. If we increase the intensity, we get to the vapor-dominated ablation process, and in this case, as you've seen in the schematic drawings, the vaporization will be dominating, and the process ultimately results in a more or less melt neglecting domain and structure, as you can see in the final picture, so that the melt will play no dominant role in this process. In this more detailed schematics, you see a plot of the temperature on the surface, independence of the material depth, as you can see from the melt and heat conduction videos, scales with the root of the time, and the melt film thickness, which is defined by the isothermal line of the melting temperature at this point here. So this melt film thickness will of course get smaller and smaller the less time we allow for irradiation. This effect is plotted on the right graph in more detail. Here you see the thermal penetration depths as a function of the pulse duration, and you can see for two different thermal conductivities, kappa for aluminium and steel, that basically if we work with pulse lengths in the area of picoseconds, we get thermal melt film thicknesses of the range of nanometer to tens of nanometers, and in terms of nanoseconds, if we work with nanoseconds, we will get penetration depths corresponding melt film thicknesses of the order of sub-micron to micron. So if we really want to go to sub-micron precision, we definitely need to go well below a nanosecond in pulse length. In the next view graph, you will see a survey of several drilling processes. We classify them by two criteria. One criterion is the drilling duration, how long does it take to drill the hole, and the other one is the precision which we can achieve. And like you would expect from natural behavior, with increasing precision, the demand for more time increases as well. And that is true also for the drilling processes. We differentiate single pulse drilling, percussion drilling, trepanning, which is already something like cutting, and helical drilling, which works with very short pulses, as we will see. So let's go through these four processes one by one. I will start with the first two, with single pulse drilling and percussion drilling. So in single pulse drilling, we have melting and vaporization at the bottom of the hole. We will have solidification of the melt at the hole wall. And of course, with increasing depths, there will be higher adhesion at the upper parts when the melt cooled down already, so it will more likely adhere in the area of the exit of the hole. Then we might have some shadowing effect, as you see here in this enlargement, some shadowing effect that if the melt really forms in the hole, then we will have shadowing effects and the intensity of the incoming laser will not get to the bottom of the hole. And of course, a very important point is recondensation, which means that also from the vapor phase we get recondensed material, which we usually don't like. So those are the challenges in single laser pulse drilling, which can be overcome by tailoring the intensity in space and time. If we apply more than one single pulse, usually in the temporal range of something like a millisecond, so if we apply more of than one pulse, like seen in the right part of that picture here, this is supposed to indicate that we have several pulses which we put onto the drill subsequently. Then we get increased drilling depths up to several millimeters. And as you can see, aspect ratios can be achieved in the range of 20:1. So such holes are rather narrow and rather deep. The next process is called trepanning. And trepanning is already a motion of the laser beam. So we move the laser beam in a usually circular geometry at a certain radius. And this radius, of course, is larger than the beam radius, so that we basically really cut out a round hole, as you see in the schematics above that picture. So with this process, we can address also geometries under rather narrow angles. So this can very difficultly only be done by mechanical means. So in this case, we have the opportunity to drill holes also under rather large angles of incidence. And we also can make conical holes, as you see in this example here, depending on the way how we now guide the beam in space with this additional axis. A very flexible way of drilling holes. In this video here, you can see a online picture taken where we drill the hole, and then you can see the trepanning process. So the laser is moved around the hole and we cut it to the final shape of the hole diameter. This trepanning is applied in very real-world applications, like this drilling of thermal barrier-coated high-strength materials used in turbine blades for airplanes. And you can see here two characteristics of the trepanning process. One is that we can cut under very high angles of incidence, and number two, that the exit, in this case here in a ceramic environment, is even individually shaped. This can also be increased by further processes like ablation with ultrafast lasers. We will get to that in the corresponding video. The final drilling process is called helical drilling. So helical drilling is explained very easily by the word itself. It's like a helix, so it is a staircase-like process where pulse by pulse we walk down, so to say, a staircase, a cylindrical staircase, and that's why we call this process helical drilling. In these schematics and pictures to helical drilling, you see on the top right a footprint of several pulses under the same orientation of the laser pulse. So here the laser is simply positioned at different points on that radius which we want to drill, but the relative position is kept constant. As a consequence, as you see it in this schematics down here. If the laser is not really perfectly round in intensity distribution, we will have different parts of the laser, so to say, to touch the edge of the drill, and we might get differences in performance. To overcome this, what we do is we rotate the shape of the intensity distribution along with the position around the drill. In doing so, in this case it's exaggerated, even if we have such a peanut-shaped beam distribution, we will always have the same part, so to say, of the laser beam touching the wall, so we will get automatically a self-stabilizing process in terms of the roundness of the resulting holes. And that is one of the key characteristics of helical drilling. In this video here, you see an animation of the process. And as I tried to explain to you earlier, step by step, so to say, you walk with the laser beam down the stairs, the circular stairs of that hole shape, and get a very precise but rather time-consuming process. How do we rotate this beam? This is seen in the schematics on this picture. On the left-hand side, we have a simple wedge which we use, which deflects the beam. So if we turn the wedge, we get to a corresponding turning of the laser, however, maintaining the orientation radially symmetric to the process, which is what we want. In the right display, it's a little more complex process with a so-called dove prism. The advantage of this dove prism is that we can get a more vertical incidence of the laser beam, even though we rotate it, even more vertical with respect to the axis of symmetry, so we can get higher aspect ratios using these dove prisms, and that is why they are used in praxis. Here's a picture of such a helical drilled hole. So we get rather negligible melt formation, as I indicated. If we use pulse lengths of 10 picoseconds, well below 1 nanosecond, the melt film thickness gets well below 1 micron, so we get very good quality. And you can see that the geometry is very stable as well in these processes, because we can define it by the rotating beam. So those were the descriptions of the 4 different drilling processes, and in this view graph here we have summarized the typical characteristics of these processes. Starting with single pulse drilling, those are the quickest holes we can drill with lasers. Aspect ratios may be up to 10 to 20. Typical drilling times a few milliseconds, less than a second usually. If we go to multiple single pulse drilling, which is called percussion drilling, then we use also shorter pulses, and we have a little more time that we need, typically between 1 to 5 seconds drilling time, but aspect ratios up to about 50 to 1. And in trepanning, we have again aspect ratios 50 to 1 about, but the advantage of really getting very high angles of incidence, which we can use in these processes and still maintain a high rectangularity of the drill and have relatively short times, also in the range of a few seconds. The most time-consuming but most precise process in drilling, however, is helical drilling. We have to calculate something like a minute, but then we can get high aspect ratios, high surface quality, high rectangularity, high aspect ratios, all you want from a perfect drill. In this outlook view graph, you can see a next step in ablation and precision processing, which now uses very short pulse lasers. In this case, we use pulse durations below 10 picoseconds. And as a result, if you look at the scale in this picture here, which is 1 micron, we get surface structure, surface roughnesses in the area of 1 to 10 nanometers. So very precise way below submicron precision with these lasers if we apply them. So this summarizes the video on laser drilling, and you have seen the 4 different processes that are applied today. As a natural evolution of the consequence of reduced melt film thickness with shorter pulse lengths, people developed picosecond lasers, femtosecond lasers of real high powers up to several hundreds of watts, kilowatts, in order to scale this wonderful ultra-precision process, which we will handle and take care of in a separate video.